Now we would like to find out the TE and TM modes in symmetry slab waveguide. Consider a symmetry slab waveguide. We have the core size is D, and the core region is between half D and minus half D. The core index is N2, and the cladding subindex is N1, which is the same as the substrate index. And for guided mode, the wave should be confined in the center core region, so the field should look like in this way. The field will be guided in the center and decay in the cladding and the substrate region. So in the core region, the field should be confined, and in the cladding region, the field should be exponentially decay. And now we consider TE mode. For TE modes, we have obtained their corresponding differential equation, which is in the core region, it can be expressed as this equation. As in the cladding region, it can be written as and as I have said, to have guided mode, in the core region, the field should be well confined in the center. So in the core region, the field distribution should be sine function or cosine function. As a result, due to the field distribution should be in these two functions, this term here should be positive. And in the cladding and substrate region, the field should be exponentially decay, so this term must be negative. Okay? According to the field distribution in each region, we can write down the corresponding EY field and the HZ field. First, let's express the EY field in the core and the cladding region. For the EY field, in the core region, the field should be sine function or cosine function. So the EY field can be expressed as the superposition of sine function and the cosine function in this form. And in the upper cladding region, we have the field to be decayed. As a result, we express it in this way. And for lower cladding region, S is negative, so the exponential decay function is written in this form. Okay? And we also know that if you have obtained the EY field, the HZ field can be found out by use this equation. So, according to the EY field expressed here, we can write down the corresponding HZ field. In these expressions for EY and HZ, you may ask, what will be the value of H and Q? What is the physical meaning for H and Q? To find out the physical meaning of H and Q, let's take the EY field in each region into their corresponding differential equation. For example, take the co-region into this differential equation shown here. You can have like we just take this term into this equation. Then you will have minus H squared times psi Hx plus N2 square K square minus beta square times psi Hx, and the left hand side here can be arranged as this way. Which is 0, okay? And this expression must be satisfied for all kinds of psi function. As a result, to make sure this term to be 0, this one should always be 0, okay? For any possible solution of psi function, all of these should be 0. So the only way is make this term to be 0. As this term is 0, we will have like the H can be expressed as square root of N2 square K square minus beta square. In the same way, the Q can be written as square root of beta square minus N1 square K square. As we have known that N2K is the K vector in the co-region, right? And we know that N2 square K square can be written as the summation of KZ square plus K transverse square. This means that the N2K vector have two components. One is the Z components, the other is the transverse components. As a result, the square of N2K should be the square of KZ plus the square of K transverse. And we know that the Z component of K is beta, right? So this one can be written as N2 square times K square will be beta square plus K transverse square. From this relationship, you can see that the K transverse will be the square root of N2 square K square minus beta square. That is the H I have written here. As a result, the H is the transverse wave number. In the co-region. And similarly, you can find out the Q value is the transverse wave number in the cladding region. Besides, to make sure that the field is well confined in the center core, this means that in the center it should always be sine function or cosine function, and in the upper cladding and the lower cladding, the field should always be exponentially decay. As a result, this term shall always be positive and this term shall always be negative. So the h square and the q square, they shall always be positive. This means that h and the q, they are both real numbers. The next step is to satisfy the boundary condition. As we know, the boundary condition is the tangential components of the E field and the H field, they shall be continuous across the dielectric interface. And in this TE mode, the tangential components of the EH field is EY and HZ. So both these two fields shall be continuous. At the dielectric interface, which means that they shall be continuous at x is half d and minus half d. Okay? Because the co-cladding interface are located at s is half d and s is minus half d. So we take the boundary condition into the EY field and the H field, we can have the following four equations. As you have obtained the above four equations, you can use these four equations to form another four equation. By using the equation 1 minus equation 3, you will have the following equation A. And by using equation 2 plus equation 4, you will have equation B. Following the same way, we can obtain equation C and equation D. Using the equations in the previous slide, we can have two sets of solutions. For optical waveguide, for the separate waveguide I plotted here, we have in the center is S is 0. So we can have two kinds of guided mode. One is obtained by cosine function, and the other is obtained by sine function. Okay, so this is cosine function, this is obtained by sine function. And you can see with respect to the center line here, the cosine function corresponds to the even function. And the sine function will stand for the odd function. Okay, so the guided mode can form two sets. The first one is symmetric TE mode. Which is the even function shown here. As the guiding mode is symmetric, which means that it will be a cosine function. As a result, the A should be 0. And since the field is symmetric, the field distribution in the upper cladding should be the same as the field distribution in the lower cladding. So the C and the D, they should be equal to each other. So for symmetry TE mode, we have the following condition. A is 0 and C will be equal to D. Then, according to these conditions, we can use the equation D to be divided by equation C. Because A is 0, we don't consider these two equations, we only consider these two. And by using the D equation divided by C, you will have H tangent HD over 2 will be Q. Okay? And of course, the other set of the TE mode is anti-symmetric TE mode. which corresponds to the other function I plotted here. And for other function, it will be expressed by the sine function. As a result, the coefficient for cosine function b will be 0. And due to it is antisymmetry, c will be minus d. Okay? And in the same way, due to b is 0, we don't consider these two equations. We only consider equation A and equation B. So we divided the equation B by A, then we will have H cotangent HD over 2 will be minus Q. Okay, so by solving this equation, you will have symmetry TE modes. By solving this equation, you will have antisymmetry TE modes. But we will ask if we can just solve one equation to obtain all kinds of TE mode. Okay, to find out one equation to have the symmetry TE mode and the antisymmetry TE mode, we can use that. Okay, you can see that for symmetry TE mode, they will satisfy this equation. For antisymmetry TE modes, they will satisfy this equation. So we just combine these two equations to form this one. And then both symmetry TE modes and the antisymmetry TE modes, they will satisfy this equation. So we just have to solve this equation to obtain all kinds of TE modes. But this equation is too long and too complicated, so we can rearrange it in a simpler form. It will become tangent HD is 2HQ over H squared minus Q squared. So this one is the equation which we can obtain the symmetry TE modes and the antisymmetry TE mode. That is, we can obtain all kinds of TE mode by solving this equation. And of course, from this equation, you can see that the H and the Q is formed by can be expressed in terms of beta and lambda, right? Because it have k and beta. As a result, this equation will help us to find out the relationship between beta and lambda. So such kind of equation, we call it dispersion relation. So this equation is dispersion relation for TE modes in symmetry slab waveguide. Okay? And then I would like to define a new parameter to simplify all the expression. Here, we define two new parameters. One is U, which is HD over 2. Another is V, which is QD over 2. And clearly, by this definition, the dispersion equation for TE mode can be written as U tangent U is V. And the dispersion for antisymmetry TE modes can be rewritten as U cotangent U is minus V. Okay? And of course, if you remember, we know that H is in this way. And the Q can be obtained as this one. So clearly, you can find out that U square plus mu V square will be Kn2D over 2 times square root of 2 delta and square. Okay? And you can find out that this one is normalized frequency. So we know that the U square plus V square will be the square of the normalized frequency. Then we will use the relationship I have shown here to find out the solutions for the TE modes in the following slide.